Hypothesis test with larger sample. A couple of weeks ago, I went over a couple examples with larger samples, just to introduce you to the terminology of hypothesis testing. And then last week we went over hypothesis tests with smaller samples using tree diagrams. With this example, we're going to go back to larger samples again. And I'll start out with this example 6. In order to test whether Maddie has extrasensory perception, abbreviated ESP, Maddie was asked to identify without looking the shape on a card as either a circle, a triangle, a square, a star, or a wave. Thus, if Maddie is just guessing, Maddie has a 1 in 5 chance of guessing correctly. So there was experiments that actually, about 100 years ago actually, there was some experiments that were done that were like this at Princeton University. And they had two people. One person looked at the card and but didn't show it to the second person, and the second person had to say whether they thought it was one of these 5 shapes. So anyway, so if the person gets more than we would expect they would by just guessing, then that would be evidence that they have extrasensory perception. In a sample of n equals 60 tries, the proportion correctly identified by Maddie, p hat, 15 over 60, 15 divided by 60 is 0.25. So the null value, if Maddie is just guessing, it should be 1 over 5, which is a decimal. 1 divided by 5 is 0.2. So Maddie actually got a little bit more than she would by than she would by just guessing, but that could have happened by chance. So we want to know what is the likelihood that Maddie could have gotten slightly more than 20% correct just by chance. The other null value, the proportion that Maddie would get incorrect if Maddie is just guessing, it's going to be represented by Q, or 1 minus P, 1 minus 0.2, and that's 0.8. So with 95% confidence or 5% doubt, we want to test H0, P equal 0.2, Maddie is just guessing, versus H1, P greater than 0.2, Maddie has ESP. So we have a right-tailed test here. If Maddie gets less than Maddie would get right by guessing, we're not going to think that Maddie has ESP. We'll just think that Maddie got unlucky in guessing. But if Maddie gets more than Maddie would get by just guessing, then we might think that Maddie has ESP. So this is a right-tailed test. Okay, so first step in testing the hypotheses is to check whether n times p and n times q are both at least 5. So our sample size n is 60. And p, we're using the value of p if h0 is true. So 60 times 0.2 is 12, greater than or equal to 5, and that's a yes. And then 60 times q, that's the proportion Maddie would get wrong in the long run, but if Maddie is guessing, it's 48, greater than or equal to 5, and that's a yes. So when you get 2 yeses, that means we can use the z-table to find the approximate probabilities. Otherwise, we would need to use the exact binomial probabilities. The next step, if h0 is true, the sample proportion p hat has mean or expected value of 0.2. So if Maddie is just guessing, and on the long run, we would expect Maddie to get 0.2 right. And then the standard deviation of p hat, this formula here, sigma equals the square root of pq over n. So that's going to be 0.2 times 0.8 divided by 60. And we can put these in a calculator. So the calculator knows something about the order of operations. We can just put it in the way it's written, and then just don't push equals until the end. So we'll have second square root 0.2 times 0.8 divided by 60, and then push equals, and we get 0.05 something. 0.0516397778, and I'm going to store that in memory so I don't have to retype it into the calculator. That's the standard deviation of p hat. Okay, so now we can compute this test statistic. That's actually a z-score. You might recall from earlier in the course, the z-score is the score minus the mean divided by the standard deviation. In this case, our score is our sample proportion, p hat, which is 0.25, and the mean of p hat is going to be the 0.2. Standard deviation of p hat is the 0.0516. So it's going to be, we put in the numbers that we just computed here. 0.25 is p hat, minus p, which is 0.2, and divided by this square root of pq over n we already computed. That's the standard deviation of p hat, 0.0516397778. Okay, so the calculator does not know about the long division bar. A short division bar, the calculator knows that a short division symbol comes before subtraction in the order of operations. It does not know about this long division bar. This long division bar that goes underneath the subtraction symbol actually comes after the subtraction in the order of operations. So when we put the 0.25 minus the 0.2, we're going to have to push equals to force the calculator to do that first. So 0.25 minus 0.2 is 0.05. And then we can do our division. I stored this in memory, so I'm just going to pull that up from memory. So it's 0.05 divided by, and recall this from memory, and then equals, and I get approximately 0.97. So that's our test statistic. Okay. Okay. So so then we can look that up in the z table. Next step, step 4. Because we're doing a right-tailed test, and because our z-table is left-tailed, we have to look up the opposite sign of our test statistic in the z-table. So we want the probability of z being greater than 0.97, because it's the right-tailed test. We have a greater than symbol. So the z-table is based on a bell curve, which is symmetric. So the right tail is going to be on the right. A z-score of 0 is going to be in the middle, and anything above 0, positive z-scores are going to be on the right. And because the bell curve is symmetric, this is the same as the probability that z is less than negative 0.97. So so it's the same probability as the right tail. So the probabilities correspond to the shaded area. So we want to look in the z-table, look in row negative 0.9 and column 7. Okay. And negative 0.9 in column 7. Looks like 0.1660. 0.1660. Okay, so that's our p-value. So our p-value is a p-value is greater than alpha, which is 0.05. We'll usually use 0.05 for our cutoff point. So that means we fail to reject H naught. The sample does not provide enough evidence to say that Maddie has ESP. Okay. Okay. Strictly speaking, we never accept H naught. Either we reject H naught or we don't know. In this case, we don't know. There's not enough evidence because of the awkwardness of the language, that's sort of the double negative of fail to reject. In books, you'll sometimes see the language about accepting H naught, but technically we don't accept H naught. We either reject H naught or we don't know. Okay, so let's make this diagram. We've made a diagram before showing the possible outcomes of hypothesis testing. So either H naught is true or H1 is true, and either we don't reject H naught, or we reject H naught. Okay, so if we reject H naught when H naught is true, that's called a type 1 error. And alpha, Greek letter lowercase alpha, is used to represent the probability of a type 1 error. 1 minus alpha is our level of confidence. If we don't reject H naught and H1 is true, that's called a type 2 error. Probability of that happening is beta. I think it looks like a script B, capital B, but that's what we use to represent the probability of a type 2 error. And the probability of rejecting H naught if H1 is true is 1 minus beta. That's called the power of the test. So I sort of summarize it down here. 1 minus alpha, our desired level of confidence, usually we'll like that to be around 95%. Alpha is our desired level of significance or level of doubt. Usually we like that to be around 5% or less. The p-value, I have here actual level of doubt, but more precisely it's the probability of getting a result this extreme if H naught is true. Greek letter beta, probability of a type 2 error, and 1 minus beta is the power of the test. Okay, so some exercises. Is it possible we made a type 1 error in example 6? And so in example 6 we did not reject H naught. So we would not have made a type 1 error. Possibly we made a type 2 error. But if you reject H naught, you take a chance of making a type 1 error. If you don't reject H naught, you take a chance of making a type 2 error. So so no, because we failed to reject H naught. Is it possible we made a type 2 error in example 6? Yes, because we failed to reject H naught. The best way to lower the chance of either type of error would be to increase the sample size, but the drawback to that is that the larger samples tend to be more expensive. So there's kind of a trade-off between making some type of error and the expense of a larger sample. And that concludes this presentation.